In the second last lecture that we did, we stated the Chomsky-Evie-Schurzenberger theorem, which claims that push down automata and context free grammars are equivalent in power. In that lecture itself, we proved that for every context free grammar, there exists a single state push down automaton which is representing the same language as that of the grammar. So, for every context free grammar, there exists a PDA. That is what we proved in that lecture. And in the previous lecture, we proved that for every PDA, there exists a PDA with a single state, or in other words, a PDA with multiple states can be automatically converted into a PDA with only a single state, and thus in order to complete the proof for the Chomsky-Evie-Schurzenberger theorem, we need to show that for every single state PDA there exists a context free grammar, and that is the topic for today. And why is it enough to consider only single state PDA? Because from the previous class we know that if the given PDA is having more than one states, then we can apply the construction that we discussed in the previous lecture to obtain an equivalent single state PDA. So, it is enough to get a procedure or algorithm to convert a single state PDA into an equivalent context free grammar. And the construction we are going to discuss today and is just the reverse of what we did in the lecture L34. But we can see that formally in this lecture. So, the topic is single state PDA to CFG conversion. We can try to understand that process by an illustrative example. Consider the single state empty stack PDA A with the following transition relations that we will see for the language of strings over AV with equal number of A's and B's. And empty stack PDA means which is accepting by emptying the stack. These are the 7 transition relations in the given PDA, and you can easily check that this PDA is going to recognize this language. But that is not the topic for today. Now we have to see, given such a PDA, how can we get a context free grammar? That is what we are interested in. And now see, if you are given with an input like ABBA, which is in the language, because number of A's is 2, same as number of B's. See what is going to happen. In this configuration, the state is Q, the next input symbol is small a, and the top of stack symbol is bot. So, the transition that you want to apply is for QA bot, and here is one transition, number 2, you can apply that. And what is it saying? Anyway, only one state, stay in that state, read that input symbol small a and replace the top of stack symbol, that is bot, with a bot. So, that is what you do when you apply the second transition. Now, what is the transition that you need for QB capital A, which is transition number 6, and what is it saying? Remain in Q and pop out. You just pop, don't push anything in. So, A will be taken out and read head will be moving right, and that is what you did here. And now you need to have a transition for QB bot, and it is here number 3, And what is it saying? You replace this bot with B bot and move right. So this is what you are getting, and the next input symbol is small a. So you need a transition for QA capital B. QA capital B is here, number 5. What does it say? It says you take out that symbol, that's it. Don't push anything. So that is what you did. You just took out that capital B. Now see that you finished reading the input, and this is an empty stack PDA, so you want to empty this stack. For that, what is the transition that you need? From the state Q without processing an input when bottom is on the top of stack. So the transition number 1 applies there, and what is it saying? Remain in the state and take out bot. Okay, that is what you do. And not that now when you are executing the machine on this input, it ended up in a configuration where the stack is empty, and hence you accept this string, and that is okay because it is in this language. Now we want to get a Contestory grammar. Can we obtain a Contestory grammar whose leftmost derivation can simulate the computation of this machine for a given input? Answer is yes, you can. We can see how we can do that. Recall this example. This is the set of transition relations, and for a given input, this is the sequence of steps in the computation that we looked at. And we need to get a Contestory grammar, and I said we will be just applying the construction that we discussed in the lecture L34, but in the opposite direction. From a PDA, we will be obtaining a Contestory grammar. And if you recall from that lecture, you can see that in a leftmost derivation, a configuration like this is represented by the input symbols already processed. In this case, nothing is processed, so epsilon, followed by the content of the stack, which is just bottom. Okay, so the string representing this configuration is the string which is already processed or read, which is nothing, followed by the content of the stack. Okay, for this configuration, so bot is the sentential form in the corresponding derivation. Now if you apply this rule in the second configuration, what you are getting? This string already read is small a alone, and the content of stack is capital A bot. So what you want to get here is small a capital A bot. Okay, and now can you tell me what is the corresponding sentential form that you need here? It is the string already read AB followed by the content of the stack. So this is what you are getting. And what about this? You already read ABB followed by the content of the stack. So that is what you need in the corresponding derivation using the Contestory grammar. Similarly here, you finished off the input, so it is ABBA followed by the content of the stack. And finally, if you look at this configuration, it is ABBA followed by the content of the stack, which is nothing. So it is ABBA alone. So now not that, the corresponding derivation will start with this symbol and will derive ABBA, which was actually the input to the automaton. Now, not that in the constructed grammar, the stack alphabets, in this case capital A, capital B and bot, are going to become the variables in the grammar. So the bot is also going to be a variable. So now you have to replace bot with a small a, capital A bot. So you need a production of this kind. Bot can be replaced with small a capital A bot, because you are replacing in the derivation in a step, you are replacing bot with small a capital A bot, means you have this production, and not that production is obtained corresponding to transition 2, and that is why I am writing it here. Now if you look at here, what kind of a transition is there and what is the rule you need in the grammar? What are you doing here? The leftmost symbol is capital A, which is replaced with a small b. So A going to small b is the rule that you need in the grammar. That is exactly what you applied. Now if you look at the step going from here to there, what you did? Bot is the only variable which is going to be replaced with b bot. Okay, is it just b bot? No, it was only ab. It is small b capital B bot. So the transition you need corresponding to, this production in the grammar that you need corresponding to transition 3 is this: bot can be replaced with b capital B bot. And the second last production that you have to add, can you look at it and see what you need? You can see that you need to have or you need to replace capital B with a small a is what you do. This bottom is retained there as such. So in between you have a capital B here that is getting replaced with small a. So B going to small a is what the production that you need. And in the last step, what you did, this bottom is taken out, means bot going to epsilon is the transition. Okay, this is our observation from this processing. So if you want to generalize, look at the transition and tell me what kind of a rule you are adding. It is nothing but the top of stack symbol is going to become the LHS of the transition. Okay, the top of stack symbol is the LHS. And what is the RHS? It is the input symbol followed by the second parameter in the RHS. So in this case it is small a followed by capital A bot. And maybe you look at here, the LHS is the top of stack symbol and the RHS is the input followed by the second component in the RHS, which is epsilon. Maybe you can look at here, what is it? The top of stack symbol in the LHS, and in the RHS the input followed by the second component in the RHS. And now you can tell me, for this particular input you are not demanding to have 4 and 7, but in general you need it. So what is the corresponding production you need? LHS is going to be capital A, RHS is going to be small a followed by capital AA. Okay, that is what I am telling. Okay, so what I said is that in a rule or transition rule, how will you obtain the production rule is the top of stack symbol is going to become the LHS of the production rule, and the RHS is nothing but the input symbol in the transition followed by the second component of the RHS. So B followed by capital B bot. This is what we are telling. If you have a transition of this kind, where beta is a string of variables, we are assuming that the production is of that form, then what is the required? You always know that here it is a string of variables which will be going on to the stack. So what will be the corresponding transition by this generalized rule? Capital X is going to be the LHS, and in the RHS it is C followed by the second component of the RHS, C beta. Now can you apply this rule to get a production rule corresponding to 4? it is capital A, this capital A in the LHS and in the RHS, small a followed by capital AA. So this is exactly what we are getting here. Now one more transition is left with. Can you see what a production rule is required here? Capital B in the left side. So it is always the top of stack symbol. It is not going to be depending on whatever you have here. It's exactly the top of stack symbol in the LHS. B. In the RHS, small b followed by capital BB. So it is a straightforward approach. Now we have got the grammar, and the start symbol of the grammar is going to be the bottom of stack symbol for the automaton. So you can start with that variable, which is the start symbol, and recall again that the variables in the grammar are going to be the stack symbols of the automaton. So you are starting with bot. Now you apply the production corresponding to transition number 2. What is that production? You replace bot with small a capital A bot. So you do that. You applied the production corresponding to the rule that you applied in the automaton in its execution. And here what you applied is transition rule 6, which is this, and so the corresponding production rule needs to be applied here. It tells you that capital A needs to be replaced with small b. This is production number 6, so this is what you did. Now from here what you did is you applied transition rule number 3. So you have to apply the corresponding production. So you are replacing bot, which is the leftmost symbol here, with a small b capital B bot. So if you apply that rule 3, you are replacing this bot with small b capital B bot. And here you recall from the figure that you are applying transition rule number 5. So you need to apply this transition capital B going to small a for this capital B. So you are getting this. And from 5, after 5 you applied rule number 1. So you have to apply this production now. What is it saying? Replace bot with epsilon. See, we are now deriving the input string given to the PDA. The PDA will start with an input string, and after a sequence of operations, it is coming into an empty stack and accepting it, means in the leftmost derivation you will derive that string. So we are getting an illustrative example to see that you can construct a Contestory grammar which can simulate the leftmost derivation, whose leftmost derivation can simulate the computation of the given machine on an input string. And this is a generalizable procedure, and we can do it to get an algorithm. So what is the algorithm for single state PDA to CFG conversion? Given a single state empty stack PDA, a single state alphabet set, stack alphabet set, start state is the single state, transition relation, and bottom of stack symbol. From that we can define an induced grammar induced by A, such that the language of the grammar constructed and the language of the given automaton are same. How will you define? Without loss of generality, assume that capital S is not a stack symbol. How can you assume this without loss of generality? Because if you have a stack symbol with name capital S, you can rename it. Rename that and rename and accordingly change all the transitions by affecting the renaming. You can do it. So, without loss of generality, assume that S is not a stack symbol. Now, you can define the infused Contestory grammar as this. A grammar is a quadruple. This must be the terminal symbols. This must be the set of variables, set of terminal symbols, the start symbol, and set of productions. And what is the set of variables? It is actually the stack symbols minus bot union S. So, what we are doing is we are renaming bot as capital S, because we used to have capital S as the start symbol of a grammar. From the previous example, we know that bot is actually the start symbol, but you can just rename bot as capital S is what we did. Otherwise, it is same as the set of stack symbols. So, the variables are nothing but stack symbols of the automaton. And what is sigma? Which is the finite set of terminals. So, the terminal set of the grammar is going to be the alphabet set of the automaton. And start symbol is capital S, which is nothing but the new name given to bot. And P is the finite set of production rules defined by the rule that we observed from the previous slide. This is the rule. If you have a transition like this in the automaton, then you add a rule in the grammar. What is that rule? Capital X going to C followed by beta is what we said. And when you are adding these production rules, you have to make sure that wherever bottom is there in the transition rule, you are replacing it with capital S, because we did that here. So, this is the algorithm, which is actually the reverse of what we did in lecture L34. With this, we are coming to the last slide of this lecture, where I am giving you an exercise problem for you to practice. How can you obtain a Contestory grammar from a given single state push down automaton? But that again is left as an exercise. You have to come up with a single state push down automaton accepting this language, then apply today's algorithm to obtain the induced grammar, and once after you get the grammar, you do the computation of the given automaton or the automaton that you are giving on these inputs, and parallelly you look at the derivation process also. In each case you can see that the computation of the machine is simulated by a leftmost derivation of the grammar that we constructed. Today we looked at an algorithm to convert or to obtain an equivalent Contestory grammar from a single state push down automaton. And in the previous lecture we have seen an algorithm which will convert a multi-state push down automaton into a single state push down automaton representing the same language. And thus now we can conclude that for every push down automaton, there exists a contestory grammar, because for every push down automaton, from the previous lecture we know that there exists an equivalent single state push down automaton, and from today's discussion now we know that for every single state push down automaton there exists a contestory grammar representing the same language. And what we have obtained as a grammar is a grammar in Grayback normal form. And with this, we are completing the proof for Chomsky-Evie-Schutzenberger theorem 1962. And thus, we established that contestory grammars and push down automata are equivalent in power. Thank you.